No? Okay. Um, well, we've looked at this figure many, many times. And we will make a transition today because rather than talk about this architecture of the initial distribution of a non-aqueous fluid, which can be, for our interests, be lighter than water or denser than water. We also found out last time that the non-aqueous fluid could also be air. Um, when we talked about the vadose zone, it follows the same rules in terms of these two very important behaviors that we're interested in. And the two important behaviors I think that we're interested in follow pretty closely to these figures. And so just to recap before we start talking about our next part, and of course the next part is in contaminant hydrology, so we'll cease to be less interested in the portions which relate to the architecture of the free product, which is a really important part because it's basically the source for the contaminant stream that gets dissolved in water and ends up going downstream. We'll be interested more in the advective flow and what gets carried with that advective flow as a plume travels downstream. So we know that this behavior that we have here has a couple of important components. We know that we can use these two curves, which I'll draw one on top of each other quickly, I guess. See how quickly I can do it. Getting much better at this as time goes on. You know exactly what these curves will look like and what they say about the system. You've played around with them some yourselves. And that is that if we look at the saturation of the wetting fluid, and we know that these relationships look something like this, where this is either capillary pressure or elevation. And we know that this is relative permeability that will look something like, how do I do this? You've seen it many times. I'll just try and do this a bit more neatly than I usually do, just to make the point that these curves look something like this and like this. They follow exactly the same characteristics as we've talked about elsewhere. Relative permeabilities vary between 0 and 1. And so we basically have these saturation versus capillary pressure curves, which say something about what the architecture of this looks like. And you've done an example to be able to define that. And we know that we can relate elevations in the subsurface to these capillary pressures by our swimming pool analogy, both pressures going down as you go below the water table and pressures in tension as you go above it. So we know that we can link these curves directly, this vertical axis here to elevation, hence this comment here, and this concept that we can get this architecture as we go in depth. And we know that we can link relative permeabilities also to saturations. And because we can link depths to capillary pressures, and we can link capillary pressures to saturations, we can also link saturations to permeabilities. So that means that we can also link elevations to permeabilities as well, because permeability is a function of saturation, and saturation is a function of elevation. And so these two behaviors that we have allow us to do a couple of things, right? We know that this defines the architecture, for want of a better word, of the free product. This picture here, and we've spent a decent amount of time talking about that. And we know that if we want to remove it, then the rates at which we remove it are controlled by Darcy's law, which is something like a relative permeability, which is a function of saturation, a permeability, a viscosity, and I won't write it in terms of head, but I'll write it in terms of pressures. And so we know that these are the controls on the behavior. So this allows us to define a Darcy flow. So a volumetric flow is equal to a cross-sectional area multiplied by a Darcy flow, which you've used in your assignments. This is from Darcy's law. This is indeed Darcy's law here, of course. And so if we wanted to use this, we can say something about what is going to be removed from this. And you've already done an assignment to make that point. And the point is that if you wanted to calculate the mass removal rate, which I think in our classes or in our talks, our conversations together, we've called m dot, a mass rate, then this has been equal to volumetric flow rate and its maximum magnitude can be a solubility. In other words, a rate, meters cubed per second, multiplied by kilograms per meter cubed. In other words, the essence, by definition, a mass removal rate. And that's, I think, the essence of assignment 4, I guess, which you're in the midst of right now, is looking at that. And so that's really what we're going to talk about now. So we've done maybe one of the big hard parts, and that is looking at the architecture of what this looks like. We realize that this isn't going to be moved anytime soon because of what we know about different saturations. Funicular saturation is when you get a bubble of the napple sitting in the middle of the pore. No matter how fast you wash water through that pore, it's not going to carry that bubble along with it. And so the only option you have is to dissolve it in water, as kind of shown by this stippling here, and carrying it downstream. And so there are perhaps a couple of things that we can ask about this. The first one is this mass removal rate, which is this. So that's maybe the first one. And the second one could be the RTD, the residence time distribution curve, or arrival time.
Is it solubility in milligrams per liter?
Yeah, just different units, right?
Oh, okay.
So milligram would be a mass, and liter would be volume. So this is mass per unit volume. Yeah, it is often quoted that way. So it would just be different from this by some orders of magnitude, right? Conversion. Okay. Yeah, keep the questions coming, man. We've got to get a conversation going here. Come on. What was I thinking? What was I thinking? So, and you've already been exposed to residence time distributions. You know, for instance, that if this is at Darcy velocity, we know that advective velocity is equal to the Darcy velocity divided by porosity. Or this would be the Darcy velocity divided by the volumetric moisture content, which we talked about last time for Brooks-Corey. And so we can always calculate exactly what that would be. And if we know that a velocity is equal to a length over time, then that gives us two different things. It gives us how far it would go in a given time, which by just rearranging this would be that the length traveled would be equal to the product of advective velocity, always advective velocity times time, or the time of arrival, would be equal to the length divided by the advective velocity. Just rearranging the units of velocity as length over time. So that gives us something that would look like if we had, for instance, a piece of core, which could also be an aquifer, with some stuff being carried downstream from a reservoir at the top. And if you monitor if you do two things. If you monitor exactly along this flow path what the concentration looks like, the calculations that you've done so far have basically said if you look at a concentration from 0 to a relative concentration, so if the upstream reservoir was at some concentration C0, then the profile along here would look something like this. This is X. This is the first of these curves, which is the distance traveled is going to be just equal to the advective velocity times time. And if you looked at what the RTD curve was, it's supposed to be vertical, the same relative concentration between 1 and 0, where this now is time, would just be the converse of this. It would be something that looks, I suppose, I really like these different colors, where this time here, the breakthrough time, if you like, at this particular location would be equal to this, the length traveled of the advective velocity. So that's our next adventure then. So we know something about what's going on in this material. I'll bring it up again, don't worry. We know what's going on here in terms of this architecture. We have water flowing through it. This water would be flowing through it at some Darcy velocity. If we knew porosity, we could convert that to an advective velocity. And regardless, with those two pieces of information, with this volumetric flow rate here or the Darcy velocity, we can calculate two things. For sure, we can calculate the mass removal rate, which is something you've done. And we can also talk about the time it arrives. So those are two things that we might want to be able to do. And that's what we're going to spend our time now doing. Okay? Everything we've done so far has been very simple in that we've had these plug flow curves. And the plug flow means that if you look at the front of this propagation in your aquifer or in your core, it will always have a sharp front to it. And if it has a sharp front, when it arrives as a sharp front, the concentration will go from 0 to 1. And you did this example for Yucca Mountain and Longstreet, where if it goes down different pathways, it'll arrive at different times. And maybe you have a stepped front due to different velocity or different rate pathways. But so far we haven't really dealt with that in a systematic way. So that's what we'd like to maybe embark on today. Okay, got to go back here. So our interest then, so that's kind of the recap, I suppose, of what we're talking about. What we'd like to talk about are the mechanisms by which this dissolved component ends up going downstream. So we'll spend most of our time talking about transport mechanisms. And there are two basic transport mechanisms. The first is by diffusion and dispersion, which we'll talk about. Diffusion being a chemical process, dispersion being a mechanical mixing process, and advection being the rate at which is carried down by the bulk motion of the fluid. Mixed with these, but not really classified as a transport mechanism, would also be things like retardation and attenuation. And so that refers to the fact that as it flows through, as water loaded with a solute travels through a porous medium, it may have an opportunity to come out of solution and attach itself to the solid grains which is flowing past and be removed from the flow field. So the first set of transport mechanisms we'll talk about will be referred to as conservative transport. Very topical these days, perhaps. Did I hear a titter? Yes, very good. You can't help yourselves, can you? So, conservative means that mass is conserved. Mass goes into the flow field, it's dissolved in water. As it travels downstream, it's always present within the fluid, the liquid in this case. It doesn't come out onto the solids as a solid state, and therefore its mass is conserved. And so that's useful to know because this will give us the highest concentrations and the earliest arrival times, because all of the solute that's contained in the water remains in the water and is not removed and placed on the static substrate that flows past. And so conservative transport is the first one for us to deal with. It assumes that both retardation and attenuation are zero. Absorption is zero. And so we'll talk about these in that context. So those are the mechanisms by which things move. The mechanisms by which entropy increases, as it always does in the universe, and things are spread out, is by dispersion. Dispersion due to mechanical means, and dispersion due to also diffusion added onto it. So we'll talk about mixing through a variety of means. So that's our trajectory for today. So I always use, well, so this is the problem we're solving. I guess we've kind of introduced the fact that that's indeed what we're doing. We know exactly what we're looking at. We'd like to know from this chimney that we have here, and also this lens, if we have water flowing past it, what is the potential for it to pick up solute and carry it downstream? And the things that we'd like to know are, what are the concentrations at all of the locations within this plume that develops as a function of time, presumably it'll get larger with time. And also, if you have a compliance location where you're taking water out from downstream, when does stuff, bless you, when does stuff arrive? So if this is time, when is it that it arrives and we have to worry about it? And so that's the deal. The two mechanisms that we'll spend time talking about, we can maybe describe in a relatively straightforward way. We've talked about one of them, advection, and that is exactly that the advective velocity is equal to the length traveled divided by the time it takes to travel. And so we can draw the residence time distribution curves for that, and that's useful. The other transport mechanism is one which looks at spreading, so that we could maybe think about advection as plug flow. In exactly the same way that we talked about a core. If we looked at some length along that core at a given time, then the concentration might look like this, and the residence time distribution at this downstream location might look like, just drawing the same diagram I did before, not a very good diagram. Time versus concentration. Well, this is 1 and this is 0. And so the same ideas, plug flow only. So that's advection. But there's actually a simpler description, I think, of advection, which we'll come back to in a second. So the other option is to think about diffusion and mechanical dispersion. And so if we think about diffusion first, to me the easiest way to think about diffusion is to take a beaker of water, no sand, and into that beaker you put a drop of ink. And you know that initially when the ink sits there, it's if you drew a profile across this in terms of the concentration of ink, maybe with radius, then the concentration, I think, would look like Manhattan, or a portion of Manhattan. Bless you. And so that is at time t0 when you put it in. And if you look sometime later, then the mass, if you like, under here would be the same, but it would spread out. And as time continues, it spreads further and further out. Ultimately, the beaker would be filled with something which would be a very light blue. It'd be at low concentration. It'd be relatively uniform because it's what Fick's law is trying to do, is get rid of this very high gradient, dCdr. And you know that Fick's first law, you can write as a diffusion coefficient times a concentration gradient. So in this coordinate system, it would be dCdr. So dCdr here for this blue curve is very high. It's infinity, right? It's a vertical line. And so it's driving a very large flux, which means that it's getting spread out. So initially it gets spread out very quickly, and it slows down over time because this slope slowly changes. And so if you think of this now in a porous medium, and you put this ink blob in the porous medium, then this initial distribution of Manhattan will move out, even if it's just sitting here in this porous medium. So you can think of it as a beaker, you can think of it as a porous medium, it doesn't really matter, it's the same behavior that's occurring. And so with the passage of time, Fick's law just means that this spreads out. What the difference between diffusion and mechanical dispersion is that if you think about moving this beaker across the room, and as it travels from location to location, so in other words, this occurs just in the beaker, same place, you look at it, half a day later, instead of this blue curve, it looks like this red curve. If you take the beaker and you physically move it across the room, at the same time, this diffusion is occurring. And so it goes from looking at this upstream as it travels downstream, and if you took a snapshot not at the upstream location, but at the downstream location, then it would look like this red curve. And so mechanical dispersion is something that looks like diffusion, because if you didn't know that you traveled downstream, but you thought you're still in the same location, you'd think it had just diffused. But the mechanism by which it's done this is by this tortuous spreading. So the flow paths of the water as it goes downstream have gone down these different pathways. It's meant that it's carried the solute with it, and so that downstream it looks like this. And so advection and dispersion, but often these are termed just dispersion, are the apparent spreading of the solute due to two different mechanisms. One is by chemical Brownian motion, and the other one is by mechanical mixing as it's gone down this path. But the main point with it is that to an observer, if you've carried your beaker downstream from this location to this location, you don't know whether it's been chemical diffusion or mechanical dispersion that has resulted in this, because the effects look exactly the same. So they're lumped together, but they're driven by two different processes, I guess is the point to make. So when we look at transport mechanisms of dispersion, we include both of these two terms together. But we deal with them slightly differently when we deal with them, okay? And so that's what we'll attempt to do. So what we'll do is we'll talk about diffusion first, we'll talk about dispersion second, and we'll talk about advection as the mechanism to do it. So how they're combined is that this is chemically based, this is mechanically mixing based, and this relates to the physical translation of the beaker across the room as it goes from this location here to this location downstream. So that's how we'll tie them together. So we'll talk about the controls on that, and the controls for the first one anyway in terms of diffusion is by Fick's law, which we've kind of introduced already. And it says that a mass flux is driven by a concentration gradient. And the scaling relationship between them is provided by a coefficient that describes that behavior. So in the same way that through Darcy's law, we have a velocity of flow is equal to, is driven by a pressure gradient. And the coefficient that defines that flow is permeability and viscosity. And it also has a minus sign in it because the flow occurs in the opposite direction that the gradient is. So this is a positive gradient here, but the flow is in the opposite direction. So this term really represents that. So it's like Darcy's law. And this coefficient of proportionality is just referred to as a diffusion coefficient, has units of length squared over time, meters squared per second. And so what we can use is we can use Fick's law that describes exactly the rate, how we move from Manhattan to being these rolling hills, to be able to describe the process by one other relationship. And this other relationship is a relationship which defines conservation of mass. So I'm not particularly worried about these equations or your understanding of it, but just to put it in context, maybe give you some rationale why you've talked about these things in the past. Conservation of mass, you know, basically says that accumulation equals mass in minus mass out. You can often write these in differential form, and you have done in your past. You might remember it if it's not too painful. And this says that the change in concentration in this bucket, this differential cube, occurs at a rate which is the difference between the stuff coming in. If it comes in at the same rate it goes out, there's no accumulation. If it comes in faster than it goes out, then there's a net accumulation, and the sides just take care of this. And so this is just a statement of that. And so this law, Fick's law that says how quickly mass travels driven by gradient, you could imagine plugging into this to represent gradients in the x direction, the y direction, the z direction. It's not particularly important. And if we do that substitution, we end up with an expression that looks like this. It says that if we simplify it from this three-dimensional form to a one-dimensional form, this term is just the same as this. Accumulation equals mass in minus mass out. But this is the mass that comes in due to diffusion. And it's a second order PDE. That doesn't really matter particularly. It just means that we can apply boundary conditions to it, and we can solve it for some geometries that might be relevant to us. And a geometry that might be relevant to us would be this piece of core with an upstream boundary condition that is suddenly turned on at a concentration 1, and we want to know how quickly that works its way down the core and what it looks like if we take a snapshot at it. Is it really this plug flow, or how long does it take to arrive at this downstream location? So that's the one thing we can do. So hopefully we can solve this equation to be able to say something about it. And really we'll talk only about this one-dimensional system. The equation that we derived is really for a beaker with no soil in it. But if you think about having a beaker now which is filled with soil, which you now put your ink drop in, you can imagine that when this spreads out, as it did before, so remember these profiles, this is like a grade point curve, right? This Gaussian distribution turns out to be a Gaussian distribution. Then if you imagine that Gaussian distribution having to spread out, but not in water, which can go in all directions, it has to go within the pore space that is open between grains, then you can imagine this, drawing this in kind of perspective, that this axis here has to weave between the grains as it spreads out, and the pore distribution, the Gaussian distribution, gets corrupted by the fact that it has to go through this constricted pore space. And so what you could do is we could use an effective diffusion coefficient, which we'll call D star, which is equal to the textbook diffusion coefficient of a solute in water. You can look it up in a encyclopedia. Diffusion coefficient for salt in water is typically of the order of 10 to the minus 9 meters squared a second. They're all around this number for any chemical compound. If you look at how quickly it will spread in a porous medium, not in a beaker, then you have to add some correction factor. And this correction factor accounts for, as it spreads, it's going through this tortuous flow path, and it can't go directly as the crow flies between where you put it and where it wants to spread out to. And so this number you'd expect to be smaller than 1 because it's impeding the flow. And it's often, you can get magnitudes for this. It may be a half, it may be a hundredth, but you can get magnitudes for this as a function of the geometry of the pore space you'd have. But the point is you can get that number. So you could also measure it, but it's going to be less than the true diffusion coefficient of that solute just in water in a beaker. So we can do two things. We have an expression to say how quickly this might happen, and we have a coefficient which governs it. We know how to get that coefficient. It should be d star in here that says this, and we can get it as a function of the true diffusion coefficient. If we wanted to solve our particular problem for diffusion, then in one-dimensional flow, what we might want to do is to have a core which has this reservoir at the upstream location and a distance along the length of the core, which we'll call x. And we could think of this as C over C0. And if this starts off at some concentration, then for advective flows anyway, right, we knew that it would look something like this. Should make the case that this is advective. But we're looking at diffusive flows. So if we solve this equation that we've just derived, the one-dimensional equation, for this particular boundary condition, and the boundary condition is one that all of a sudden at time, this is time, we turn it on instantly at some time t0, and we keep it at this concentration forever. And this would, if there was flow in here with some velocity, then this would what this would look like. But what happens if this velocity is 0? And so there's no advection. It would say that for all time, the advective transport would be 0, and so this would never actually go into the core whatsoever. But it does. It travels by diffusion. And so if you solve this equation for that particular boundary condition, turning it on at time t0, then the solution of it is this. Happens to be a standard result. I'm not sure you'd ever have to, we might play around with it in class. It's equal to the complementary error function for the distance downstream. So this would be, bless you, this would be the distance downstream. This would be when it would arrive. And this would be this effective diffusion coefficient. So the concentration depends on the upstream concentration, how far you are downstream that you want to look at this, the material property, the diffusion coefficient, and when it is that you look at it. And if you solve this equation and draw it out, then it looks like this. It always keeps this relative concentration of 1 at the upstream location, this value here. As you go downstream, ahead of this front, it would be 0 flux. But I guess the important thing is that with this 0 velocity, it does not give us a solution where there's no motion of this blue fluid downstream. It diffuses downstream. And it would look like this. This is the profile of what it would look like. So it's a standard result. It turns out that this error function here is basically, I don't really want to it's basically a cumulative probability distribution. And so if you think about this, this would be number of components. So this is a grade point curve, right? This is the grade buster here with 110%. This is less than that. And these are the cumulative number of people. And so if you look at the area under this curve, this would be 100% of the population. The area under the curve to this point here would be 50% of the population. So this is number of students versus their individual scores. And so this 50% mark is the middle of the distribution. If you draw this as a cumulative distribution, start here and just draw the progressive area underneath this curve. And starting from this point, this is what you get. This is the 50% mark here, which is the mean, which is also the mean concentration. And these parts of the distribution, one standard deviation around the mean, are these amounts. And so stretching this Gaussian distribution into this cumulative probability distribution just gives us behavior. So that's physically where it comes from. This is what this expression is. Probably doesn't matter to make this connection, maybe curious, but what this will give you is that if you look at this curve at some particular early time, it would be quite compressed. And so this is the upstream location here, 0, and this is the relative concentration. So if you looked at this curve at early time and imagine compressing this, then the distribution will look something like this, T early. And if you look at a later time, it'll look like this. If you look at it very late, it will look like this. So if you imagine this curve just being scaled, stretched out, or compressed, then that's really what this expression gives you. At early times, this is 0, and this number is large, and it gives you this curve close to the axis. At late times, this is very large, and this number would be very small, and it would give you progressively flatter and flatter curve. So that's just the geometry. So maybe the important take-home fact from this is that if you have this diffusive equation, which includes Fick's law and conservation of mass, you apply a boundary condition to it, even if there's no velocity, there's some transport of solute downstream, and that transport, that spreading grows with time, even though the velocity here is equal to 0. And it will always look like this expression. So that's the first of our observations. So we made the case that diffusion is one of the transport mechanisms. The second one that we've talked about that gives us this plug flow is advection. And so I think that's what we look at now. Yes, indeed. We can apply exactly the same concepts to this. So advection. We have a flux, advective flux. The flux is equal to, if you remember that the Darcy velocity is equal to, sorry, we've written this. The advective velocity is equal to the Darcy velocity divided by porosity. That means that the Darcy velocity is equal to the advective velocity times the porosity. Just taking these two standard results. So you can think of the mass that's traveled by the solute dissolved in water. Before it was by diffusion, Fick's law, remember? We said that the diffusive flux was equal to the diffusion coefficient times the concentration gradient. If we look at the flux that's carried downstream, the amount of solute dissolved in water that's carried downstream, it's carried down by the Darcy velocity. And I guess you could surmise that, right? Because you remember that if you calculate the mass flux, you use the volumetric flow rate multiplied by the solubility, which is the same as the area times the Darcy flow times the solubility, right? So that's really this term here. And this is the concentration. So this term here is Darcy flux and concentration. It's actually just the same as this term here, really, but written in kind of a differential way for a flux in the x direction. So this is the Darcy flow, and this is concentration. So nothing different from what you've done before. If you take this and you take the same conservation equation of accumulation being equal to mass in minus mass out, and this time not for diffusion but for advection, where this flux here is the advective flux, and you do this and you rearrange it, so exactly the same procedure as before, then we end up with an equation that looks a bit similar to before. Has three components as before, but again, if we're interested in one dimension, then we can just take one part of that, and we will take just one part of that. And this is saying that the rate at which we accumulate stuff, so mass in minus mass out equals mass accumulation, mass rate of accumulation. So the mass rate of accumulation is how quickly it comes in relative to how slowly it goes out as an advective flux. And so you'll notice now that this dc dx is only a single order partial differential as opposed to a second order. So it's just different. But what we could do, and let's do it. Let's add these two components together. So this is due to the accumulation due to the advective flux. This is the accumulation due to the diffusive flux by diffusion. Let's add them together, put them together. And if we do that, then we end up with actually the one equation that we'll really use in this class, which is this. D star, second order concentration with length, dx squared, minus advective velocity, dc dx. So you'll see this term here. And this will be the expression that we use. And so I'm not worried that you guys be partial differential whizzes. That's not important to me, probably not very important to you either. But it's probably important to understand exactly what these physically mean. And so this is the diffusive term. And this is the advective term. And I suppose we should also make the case that if you wind back your minds to what we talked about maybe in the first 15 minutes today, is that this Fickian diffusion spreading of water in a beaker looks exactly the same as if it flows through a porous medium and gets agitated, mechanically distributed by its flow through these portions. So this is the diffusive term, but it's also, as we'll find out, a dispersive term as well. So dispersion being this kind of mechanical mixing. So anyway, so if we look at these behaviors and solve that equation on the top left in this one-dimensional form, then we end up with this figure that we have here. I'm not sure if I'm able to write on the side. I guess I can. So if we take a core, and we have this core so that it physically looks like this graph here. And we have a velocity of flow along this. And we have this upstream boundary condition where all of a sudden at this upstream location, we turn on a reservoir from 0 concentration of water to 1% concentration of something dissolved in water. So from just being water, we put something in it at this upstream location at time 0. And we look at what that looks like as we look at some later time. We know that advective velocity is equal to length over time. We know that length is equal to advective velocity times time. And so we know exactly what this RTD curve might look like, which is this picture here. This is length is equal to advective velocity times time. And everything that we've known so far is that it should look like this step function. So a step function input should give us a plug flow going downstream. If we wanted to draw, well, let's leave that for next. What this term does here is physically, I guess, maybe this term here, is if this term is 0, then we only have this advective term, and exactly the behavior we get is exactly this RTD curve that we know, you know and love so well. If you turn on this magnitude so it's non-zero, then as you begin to have a small value of this, it'll give you this spreading around the front. And as you increase this value of D star, it will give you a flatter and flatter curve, but one which for now, let's assume that it always passes through this 50% mark, the average concentration, average input concentration. So this would be D star equals 0, and this would be D star equals large. And this would be D star non-zero, but not so large. And so physically that's what it means. It gives some idea of this spreading. And you'd kind of expect that, right? Because if you think about physically what this means, if there's no flow velocity, then you get this diffusion that occurs. And so if there is a flow velocity and it's moving the front ahead, you'd expect that you'd get this diffusion or dispersion that occurs ahead of this plug flow front. And so that's the physical manifestation of that. If you looked at the RTD curve, which would be this concentration versus time rather than space. So this is the upstream boundary condition. This is the flow domain. This is the downstream arrival behavior, if you like, on the right-hand side. Physically, this is going to look exactly the equivalent of this. So if there's no diffusion, it'll look like this. If there is diffusion, it will look like this. And if there's a ton of diffusion, it will look like this. So it follows this behavior exactly, as you'd expect. So this, I don't know if it'll write on here, D, oh, it does, large. D star 0. And so these are for the cases where the velocity, advective velocity, is not equal to 0, right? So that's why you get this plug flow. Otherwise, you wouldn't get that. So the other way to think about it is if you have a source which, instead of once it's turned on forever. And so I guess if you looked at this behavior here, so once this gets in place, it's going to dissolve into water. It's going to keep on dissolving as long as it has stuff there. And I think in your assignment that you're doing now, you're probably going to find out it takes a really, really long time for this to get dissolved out and carried downstream, so it's depleted to 0. And so you can think of this as a source that gets turned on and stays on. So that's basically this condition here. Turn on, stays on for eternity, and this is the geometry you get. If you have a source that was a finite source, I guess, yeah, okay, I guess it would be one of these, right? A finite source might be this one, where there's much less in place because it hasn't gone so deeply. And so maybe if this was a smaller mass in place, then it would dissolve and then it would disappear. And so that would be akin to being this response here. So it gets turned on, it's on for some finite small period of time, and then it's dissolved and disappeared. Then you can do the same mental exercise to think about what the what the distribution would be in the core. So in the core, at some time t, it's traveled this far downstream. It looks like it's been turned on at the front. It's been turned off at the back as it's gone out. And if it's plug flow, it would be this red distribution. If you have dispersion, then this case here would be, I guess, this, the dotted line in this case. No, actually the solid line. This would be D large. This would be D0, D star if you like. And the taller one would be intermediate. And if we just use the same color for this lower one, the residence time distribution would actually mimic that. So concentration, time, Manhattan versus the rolling hills of what I do versus the rolling hills of Pennsylvania. So this is D large, D equals 0, and again, advective velocity not being equal to 0. So that's physically what's going on. So it's fine to understand where these expressions come from, this top left expression. It's better probably to understand physically what the implications are of these two different terms. An advective term, which gives you this plug flow, which would look like Manhattan or a cliff in terms of the residence time, in terms of the distributions in space and in time. And if you add this diffusive term, all it means is that some of the fluid can get ahead of you. And if some of the solute gets ahead of you of this front, then it means that some water has to get behind the front because there's conservation of volume, if you like, behind it. And so you can imagine exactly what these systems look like. And the reasons that we want to have differential equations that describe those behaviors is that we can solve these to actually say what these curves look like. Take this on trust for now, the fact that this location is equal to this length, you've used it, and that this crossover portion is at 0.5 concentration. It turns out that that's not true, as we'll see later. And so we'll find out the constraints as to when this is true, that it goes through this point, and when it doesn't. And so we don't need to deal with that now. So, making this point, we've said that there are these two different behaviors that we're talking about. Advection is one mechanism of transport. Diffusion and dispersion are one mechanism of transport. We've said that diffusion and dispersion look like each other, and that's why we classify them together. And so let's delve into that maybe a little more to understand exactly what those mechanisms might be in a descriptive sense. And so this is to make that point. Okay? So you can imagine that you could have a number of different reasons why you might have mechanical dispersion. One is if you have mixtures of grain sizes. Mixtures of grain sizes would give you mixtures of pore throats. We know that larger pore throats, like in your Yerke Mound example, would give you larger flow velocities, and smaller pore throats would give you smaller pore velocities. And so if you look at the relative rates at which you get fluid going through those, then kind of on aggregate, on a heterogeneous medium, you'd have slow pathways and fast pathways, and therefore you'd get some spreading of this front as you move through it. If you have mixing that goes in different flow paths as it weaves its way in tortuous flow versus less tortuous flow, you'd also expect to get different kinds of mixing. And as you look at even kind of the microscopic level, If you think of a pore throat as being a tube, we know that a tube has zero velocity at the edges of the tube and a maximum velocity at the center. And so if you attach fluids that's dissolved in that water at each of those locations, then they'd be going at different rates depending on where they were in that tube. Center of the river versus the bank of the river be slower. And so you'd expect that you'd get some spreading as a result of that. So if you take all of these mechanisms together, you can imagine that just as we talked about diffusion within a beaker due to chemical means, Brownian motion, is exactly the kind of behavior you'd get if you look at taking a cross-section at the source location and taking a cross-section where it is downstream, where you'd expect to have this kind of Gaussian spreading occurring. And so this spreading looks exactly the same as spreading by Brownian motion, but it's due to a different mechanism. If you looked along the length of this flow path, then for the same reasons that this is physically spreading out wider and becoming more diffuse at this front, you'd expect to have the same behavior as you look along the flow path. And so this response that we've talked about in these little curves, plug flow would be this vertical component. More and more dispersion means that this front gets canted over progressively more and more. And it would get canted over more and more if the dispersion was larger, or you could imagine if it had more time to go downstream to get spread out, then you could imagine also, as you looked at a later time, further downstream, then again, this profile might look like this, where this slope here slope, merely as a consequence that in traveling from this location to this location, it's taken more time to do it, and therefore diffusion would mean that it would be flatter because of this kind of behavior here. Steep, flatter as it gets further advanced in time for a static location. But also, in this case, the reason that it might have been a more gradual, a more gentle gradient is that instead of having more time to do this, it's had more pore throats to go through in this kind of mixing, and therefore it would be flatter. So the point is that diffusion and dispersion are very similar. They look the same, and they can be classified together. But this behavior is not diffusion, it's dispersion. It turns out that we can classify this behavior by what's referred to as a coefficient of dispersion. And this is given a magnitude in the longitudinal direction, which governs this behavior here, and also in the transverse direction, which is alpha t, has units of length, which would be this, the coefficient that controls this behavior. So in other words, how much it spreads out this way versus how much it spreads out this way. So longitudinal and transverse. So you have flow occurring in this direction. And it turns out that we can define the magnitude of this dispersion by multiplying this physical property, alpha L or alpha T, by the flow velocity. So if we know, for instance, the advective flow velocity, which is only in this direction, in the longitudinal direction, the advective velocity in the transverse direction has to be 0, right? This is a vector, has a maximum value here, orthogonal to that vector, it has to be 0. So we can get the longitudinal dispersion, which is just the product of this property of the porous medium, multiplied by how quickly the flow occurs. Double the flow rate, flow velocity, you'd get more dispersion because you'd have more mixing occurring. In the transverse behavior, double the flow velocity. This is a material property, and this is the flow velocity you find yourself going at. And so the consequence of this is if the units of these terms are indeed units of length, meters, then if you take meters and multiplied by meters per second, you end up with units of meters squared per second, which is the same as the units that are present in the diffusion coefficient and the porous medium diffusion coefficient. So the point is that if we have these two behaviors occurring, the beaker, drop ink in it, it spreads out, that's diffusion. If you take the beaker and you move it across the room, in the time it's taken to spread out, you can think of that as being dispersion, as it goes from upstream to downstream like this. They have the same units, and so we can add them together. And so the one unit that behavior that we'll use is this idea of hydrodynamic dispersion, which combines the two effects, diffusion, which is chemical, spreading due to Fick's law, and dispersion, which is mechanical. We can add them together. They define behavior along the length of the flow. And so you can imagine that if you had, for instance, a plume that develops from a source that is here, then as a function of time and you drew contours of concentration around it, then that source, instead of physically moving downstream and looking like this, which it won't look like, instead it will look more like this. And that is because you have these two effects. You have this longitudinal spreading, which I guess would look a little bit like this, if this were concentration. Actually, it wouldn't. It would look like this, wouldn't it? Let me redo that. If this were concentration. And if you drew the cross-section across here, it would look something like this. This is in the transverse direction. I won't write t. This is y, say, and this is x. And so it's governed by this. So something that looks like diffusion, which is causing this spreading, but is composed of two parts, mechanical mixing and chemical mixing, chemical mixing. Okay, yeah, I guess that's right. So that's the essence of what we're dealing with. I'm going to go to this lower figure in a second, and that'll be the last one we look at, but this is the crux of this matter. And so this partial differential equation, which looks something like accumulation, the rate of change of concentration at a particular location, is equal to longitudinal dispersion transverse dispersion and advective velocity. Very similar to the parts we've looked at before, right? This is advection. And we know that advection is length over time. So we could rearrange that as length is equal to advective velocity times time. And so it may well be that we could look at this number here as being L is equal to advective velocity times time, in a general sense. We're still taking that on trust. And of course, this magnitude along here, this would be 1, and this would be 0, and this would be a half. So we can coordinate that. And these two other terms, I think we had them in green before. This one controls this spreading. Oh, sorry, wrong one. Longitudinal dispersion controls this spreading. And transverse controls this. And so it's important that we use things like conservation of mass and Fick's law and advective fluxes to be able to define things quantitatively. We are able to define things quantitatively, which is this expression at the bottom. Accumulation, net accumulation rate of solute is equal to that is removed by lateral spreading, longitudinal transport by diffusion, transverse transport by diffusion dispersion, and the advective flux. And that we know exactly what these physically look like in terms of their behaviors. So that's kind of the crux of what we'll deal with today. The other thing that you could think of, maybe, is this classic experiment. And the best way to perhaps describe this is the last thing we may talk about, is that what happens, for instance, if we looked at flow along a sample? We know that flow along that sample, bless you, would look something like this, if this is the length and this is the concentration. If we physically drew what that looked like, I suppose it would look like these fingers of solute going down here, so that on average, not DNAPL lenses, but on average the concentration, if you averaged it over this whole thing, where you have some fast flow path fingers, some slow flow path fingers, that the concentration would look like this here, which is kind of the way of thinking of this, I suppose. One way to think about it. And so what you could do is you could look at this longitudinal dispersion being equal to longitudinal dispersion, velocity, plus this diffusion, effective diffusion coefficient. And if we divide it by this diffusion coefficient, d sub d, then imagine doing an experiment where you took this core and you could change the magnitude of this advective velocity that you put things through with. So you could choose a value of the advective velocity to be 0. And if that advective velocity was 0, then this term would be 0. And this term would be equal to 1. Right? So if you have no flow in here, you have only diffusion going along your core, and you measure that diffusion rate, then you'd expect to recover a value of 1. So at very low values of velocity, you'd think that you get a value of this diffusion rate which is equal to 1. If you then increase the velocity and still measure this effective diffusion rate by how quickly things arrive at this other end, then you might get a series of points. And these are the points that you get. So if you increase the velocity of flow and you measure this effective diffusion rate, this longitudinal diffusion rate, then these are the data you get. If you go through this same expression and now do that as we had before, so this expression here, diffusion coefficient, advective velocity, d star d, and you divide it by d star d, this chemical diffusion coefficient, which is still this property here, then this now is much larger than 0, but these two terms here will basically cancel out with each other. So this will end up being alpha advective velocity. So this is a coefficient, and this is the velocity that you're flowing things at. These are the velocities. They're plotted in a slightly different way, but you'd expect that this curve, this gradient here, is something that reflects it. So you increase the velocity by 10 times, you increase, so if this changes by 1 cycle, this also changes by 1 cycle. So this gradient here is 1 cycle by 1 cycle. And so physically what this means is at very low flow velocities, diffusion's only acting. It occurs very slowly, and if you normalize it by diffusion, you get 1. If you look at much higher velocities, then diffusion becomes trivial. It cancels out. And this term now shows that the value of this coefficient is a constant, because it's just a constant that multiplies by this. Because now as you increase this by a factor of 10, this goes up by a factor of 10 also. And so you can define that behavior. So that's fine. All right, so that's the first commentary on diffusion. So we've made the point that now we understand a little bit more about these breakthrough curves. They don't necessarily always look like plug flow curves, but they'll change based on how much dispersion and diffusion we get. And we'll talk next time about how we can calculate the magnitudes of that, how that curve is canted over.